Go. The Spot robot from Boston Dynamics is able to dance quite well. However, we have not seen it do a pirouette yet. For our project, we decided to teach Spot how to do a pirouette, otherwise known as a spin on one foot. The Spot model is a 3D body with 4 legs. Each leg has a hip joint where it connects to the body and then a knee joint that connects the upper and lower legs.
So we based our approach off of the paper from the Little Dog Notebook from class, which I'll refer to as DI 2014. And to create our desired movements, we use trajectory optimization with direct transcription. So I'm going to walk through our trajectory optimizations, parameters, decision variables, constraints, and objective. For the parameters, we use the total time, the number of knot points, and we also have the minimum clearance, which is the height the front 2 feet must clear, the minimum clearance of the supplementary leg and the back foot, and then also this vector that keeps track of when each foot must make contact with the ground, represented as a Boolean array. The constraints are implemented at the ones, not at the zeros. For our decision variables, we can break it up into 2 different groups. The first group are variables directly related to the task, which are the time duration between knot points, the joint positions of Spot, the generalized velocities, and the contact force between the foot and the ground. For the physical constraints, these also include the ones before, but more specifically, we have the center of mass of Spot with its derivative and acceleration, and Spot's angular momentum with its derivative. For the constraints, we basically took the same ones as DI 2014 for the Euler integration, the dynamical constraints at each knot point. But for the foot constraints, we implement those at each instance where it's 1. And then also we have an orientation constraint, which Irene will go into later. And lastly, a constraint on the actual time durations, similar to the Little Dog Notebook, that they need to sum up to close to the time interval. For the objective, we found that only this simple objective worked with our SNOP solver, which is not this here. It's actually just the constraint on the positions. So this is intriguing, and we want to look into this later. We found that Spot didn't come with actual foot frames at the feet, so we had to implement our own. What we did is we first calculated the vector between the frame at the joint and the position of the foot when it makes contact with the ground. And then what we did was we just added a frame at this foot.
So in order to make our Spot rear, we used our instance variable with a minimum clearance to define when the robot needs to have its front feet in the air and how high. In order to get it to stand on one leg, we changed the instance definition to also make sure that one of the back legs was off the ground. And we were able to successfully get it to stand on one leg for a low front foot clearance, but unfortunately not for a high front foot clearance. Now, in order to get it to spin, to define a spin for the trajectory optimizer, we defined a relative angle constraint at different locations. We defined the angle offset between the Spot center of mass frame and the world frame for every 3 knot points. However, since the relative angle is an absolute value of the angle offset between 0 and pi, in order to get Spot to complete a full turn, we used relative angle between the x vectors and the y vectors of the coordinate frames. So the spin trajectory is defined by a series of angle offset between the x and y coordinate vectors, and a constraint that the offset between the z vectors are 0, so that Spot does not fall over. So here's our Spot doing a pirouette, and to make the full pirouette, we combine the rearing on one foot constraint with the spin constraint. We also reduce the time in order for it to make a successful turn. To make a big pirouette, we simply increased the height constraint of the front feet.